Concept drift, where does it happen? Okay, it doesn't happen only in markets. It happens in recommender systems, for example. Let's say that you have a movie recommender system and you're saying, okay, give me a cool movie to watch. If somebody suggests Casablanca, I mean, okay, it's a great movie, but probably you're not thinking about going out Friday night with your date to that movie, right? It's a little dated. So by its very nature, recommender systems are going to have different recommendations over time. Similarly, although much of medicine is what is called independent and identically distributed, epidemics aren't, right? Because epidemics can start and then really expand very fast. So predicting epidemics is much more difficult than, say, predicting whether the rate of prostate problems. Okay, I hope it's not too personal. And fraud also could be something that goes with as an epidemic, because the fraudsters are very good at adapting to whatever protections we have. Am I getting any bad feedback? No? No? So what I'm going to talk about today is machine learning algorithms that adapt over time. That's going to be one of our toolboxes, toolkits. Mind you, it's never going to be entirely possible to handle concept drift. If anybody has read the Black Swan book, you will know the parable of the turkey. September comes along, everything's good, we're getting fed more. October, things are even better. Early November, things are really good, right? So, late November, not so good. So, if things are really, truly out of left field and there's no pattern at all, well, we're going to not be able to do it either. And maybe people can do that better, and that's great, because, why not? But we're going to talk about machine learning methods that do adapt over time. And then we're going to talk about something similar to what are called multi-armed bandits. And multi-armed bandits is, if you think of a slot machine with several levers, and you want to figure out which lever is the best lever. That's what a multi-armed bandit idea is. And in fact, we can do more. We can weight different methods. But the bandit is going to be used where each lever is a machine learning technique. That's the second element of our toolkit. Next one is that we're going to sometimes refuse to predict. That is, our machine learning algorithm or algorithms are going to give us a whole bunch of results. And we're going to say, you know what, I'm not really sure. Okay, just to go back to prostate, since I've already initiated you on that, if you have a Gleason score of 5, right, probably you don't want to do anything, right? At least you want to maybe get a biopsy. Definitely do not do anything too rash. So the whole idea that sometimes you'll take a prediction but you won't act on it is a very important idea. And then I will discuss some experiments showing that if we do all these things, we can actually get a better performance in prediction. So as I said, we still have the problem of the turkey, but maybe we can do something when it's not so turkey-like. Okay, so the first notion is that neural nets, which are of course very popular these days, the great thing about them is they're adaptive by design. Because the way that neural nets work is that whenever you get a response, and the great thing about financial markets is that you actually know what the answer is. Let's say you decide, I'm going to predict whether I should buy this and sell this tomorrow. You know whether you were good or not, whether this was a good idea or not. And so neural nets are adaptive by design because they use this thing called backpropagation. Forgetting what the technicalities are, it's a kind of feedback. The same kind of feedback that you use when you adjust the water heat of your shower. So it's a kind of feedback, and it's a continuous feedback. And so in the domains where neural nets can work, which are usually domains where there's tons of data, then they're adaptive by design, and it's always good. But sometimes neural nets won't be so good because there's just not enough data. So neural nets have come into their own because of computer vision, where there's a lot of data. But if you have a seldom trading bond, for example, you don't have that much data. And even if you look at the bonds that are cousins of that bond, you still might not have that much data. So another technique that we use very often are random forests. And random forests have this, basically are a forest of trees. That's why they're called forests. Each tree is more or less a decision tree. You use a decision tree when you're going out in the morning. You say, well, the temperature is less than this, I'm going to take this jacket. If it's going to rain, I'll take an umbrella or something like that. Okay, so that's a decision tree. In this case, the decision trees are factors that might influence the price of some security. And random forests, because they're a forest of trees rather than a single tree, they can handle nonlinear behavior very well. So if there's some combination of factors that, due to some function that we're not even sure about, I mean, it may be quite, maybe this times that, or maybe something else, random forests can handle those very nicely if you have a decent amount of data, less than neural nets. And because there are all these trees, we have this forest, we're going to kind of judge each tree. And we're going to go, you tree, you've been telling me the wrong thing a little while, so I'm going to rebuild you. Okay, because maybe the data needs to be adapted. Or we need to adapt to that new data. So adaptive random forest algorithms can handle concept drift if, okay, again, there's still the problem of the turkey, but they can handle concept drift if the drift is happening and maybe there is a sudden shock, and then very quickly the random forest will adapt to the shock. Maybe not instantaneously, but quickly. So what we've talked about is we've talked about the base algorithms and their ability to adapt by themselves. So neural nets, as I said, do it by their very nature. Random forests can be encouraged to do it. Support vector machines can also be encouraged to do it. So all of the basic machine learning algorithms that people use can be modified so that they can be adaptive. Now imagine that you have a whole bunch of machine learning algorithms, and they are all doing some prediction. They're predicting the next bond price or something. So then the question is, the simplest thing you could do is you could say, you know what, I'm going to choose the one that's been best, which is, how many of you who run funds, ETFs or whatever, you go, well, I've been great, so you should choose me, right? So this is the multi-armed bandit for the investor, right? I'm going to choose your lever. But in fact, what we might want to do, more like an ETF, is we might want to have something balanced. We might want to have several people who we like. I think one of the speakers talked about that. We might want several people who we like, and then weight each of them. And so the multi-armed bandit says, I'm going to choose a particular lever. It's like choosing a particular investment advisor. But in general, what we're going to do is we're going to weight the different predictors. And so let's talk about that. So this is just more explicit. We have several algorithms. They have neural nets, random forests, whatever, support vector machines. We evaluate the predictions of each, and now we have feedback on the weights of those predictors. So before we had feedback within each machine learning algorithm, now we have feedback of the ensemble of machine learning algorithms. And then we weight the best performing methods, and maybe there's several of them. In the multi-armed bandit, as I said, you would just choose one, but in general, you would just want to have weights. And so I work with Christina, which is always a pleasure. And also, by the way, I have to give her full credit for the beauty of these slides. My slides are always awful, but she's really good at these things. Anyway, so we have the bond droid, and so we have lots of experts, and we're doing lots of weighting all the time. Not waiting for people, putting on weights to different methods. And so our basic strategy is this. We have adaptive machine learning algorithms, and they get weighted depending on how successful they've been. Okay, now, so those are two tools we have, right? The adaptation on the machine learning algorithm itself, the weighting over the machine learning algorithms. And now I'm going to talk about the third one, which is refusing to accept the predictions. So, okay, so I think you've all probably felt this if you haven't actually said something like this. And what we're going to look at here is a bunch of data sets, very different. Some have to do with forest cover, some have to do with coding RNA, some have to do with the beautiful games Connect 4, some have to do with handwriting recognition. Now, these are kind of easy problems in the following sense. They don't actually have concept drift by themselves, because the forest cover criteria will more or less stay the same, for example. And what is a coding RNA will more or less stay the same. However, what I want to say is, still, maybe what we can do is we can sometimes refuse to predict, and then on the remaining predictions, the ones that we did not refuse, we will do better, we will get higher accuracy. Now, we're not going to just randomly say, hey, I don't accept that. We're not going to be capricious like that. What we're going to do is we're going to decide carefully, with the criterion I'll show you in the next slide, we're going to decide carefully whether we're or not we're going to accept a prediction. And just to reiterate, these are easy in the sense that they're independent and identically distributed, meaning they don't change over time. There's no concept drift here. But look at the result we're getting. If we want to cut the native error rate by 1/2, then we might be refusing, for some of these data sets, the different data sets have different colors, we might be refusing, let's say, up to 30%, a little bit more than 30%. But for some of the data sets, we don't refuse that much. And this is getting 1/2 the amount of error. And if we want to make the error just 1/4 of what we originally had, then we have to refuse more, of course. But at least the ones that we do accept, we have quite high reliability. So this is good because if you remember the quote said, sometimes I don't want to trade, but if all the stars are aligning, well, then I do want to trade. So how do we do this? Well, I'm going to give you an example from random forests. And the idea is basically this. I look at my set that I've already trained on, and I see whether, so let's say in the case of random forests, different trees are voting, let's say that this is going to go up or this is going to go down. Okay? So what I'm going to do is I'm going to say, let's just see how different this new point is from the points I've already looked at. If it's very different, well, then I'm going to say, I don't really know. Imagine that you're, an expert bond trader, but you've really focused on mortgages, and now somebody wants to ask you about government bonds. You might say, I'm not really sure, so maybe I don't want to make that prediction. So it's something like that. That would be the human analog of this. So non-conformal means it's a little bit far from what I've seen so far. And just to be concrete, let me just show you how this goes. We have a core training set. And the core training set says half the data, historical data, and we get a random forest. And then we have a calibration set where we say, I'm going to look at the predictions in the calibration set, and if over a certain number of trees vote for some outcome, I'm going to say, okay, I'll accept that trade. So the notion of conformity says how many trees, in the case of a random forest, but for all of the machine learning algorithms, one could have something analogous, how many trees vote for one conclusion or another. And if there's enough consensus, then I will take the trade. And so if we want to achieve an error bound of, say, under 10% or something, then what we will do is we will train the machine learning algorithm on a core set, and then we will look at the calibration set where it is also labeled, we know what happened, and we will see how many trees voted for a particular outcome, and what is the threshold above which, if they do vote for that, we get no more than 10% errors. Okay, very simple idea. It's a tiny little bit more complicated, but that is the basic idea. Okay, now, what if the data is not this thing independent and identically distributed? Let me just explain this concept one more time because it's really important. Independent and identically distributed, again, an analogy would be this prostate thing, right? Whether somebody's has a prostate issue now or in 10 years, or even if it's a different person, it's pretty much the same probabilities based on your Gleason score or whatever. And but if there's concept drift, of course, that isn't true anymore. So if there's concept drift, well, then the data is not IID, independent, identically distributed. So what are we going to do then? So we still use all the machinery we had. We have an adaptive machine learning algorithms. We have weights on the machine learning algorithms. We have refusals based on voting or some notion of confidence. And then what we do is we have one more level where we might have another level of refusal. And that level of refusal will simply have to do with how well we've done after the first level of refusal. So if, for example, we're looking for under 10% error, and that first level of refusal, which was based on voting, says, okay, I like this one, we will then check to see how well it's doing. Because maybe it did well on the calibration set, but maybe it's no longer doing so well. In which case we will refuse. And our algorithm, which is called safe predict, I mean, not very good. Maybe I clearly need better publicity agent. But anyway, safe predict, what it does is it says, I will sometimes refuse even though that first level of refusal accepted. Because I think what's happening is there's so many errors, so many more than I want, that really something is wrong. And so this will be our kind of last line of defense for concept drift. Because as the concept drift happens, we'll start refusing. But then there are ways to kind of get back in the game. And so then we won't refuse as much. And so the whole architecture, which I know is kind of small and technical, and it has a block. The whole architecture looks like this, and I'm sorry for the acronyms. We have an environment, we have a predictor, maybe several predictors. Each one has been calibrated, that's the CBR thing. And then whether if it's rejected, well, we don't care about it, but if it's accepted, then safe predict comes in and says, yes, you accepted, but you've not been doing so well. And then if that is accepted, safe predict passes on it, then we actually make the prediction. So this architecture, which is really simple, just 4 stages, right? It's the adaptive machine learning algorithm, the weighting, the weights on the different algorithms, the conformal prediction, which says we look at the votes, let's say in the random forest case, and safe predict, which says, still, even if you voted well, I'm still going to maybe not do it. Okay, so I've told you all this story. You might say, oh, very nice. It's typical academic. He tells us all this stuff, but maybe it doesn't work. And it may not work. That is true. So what we did here was we just looked at up and down predictions. This is kind of new work, so excuse me that it's sort of raw. We looked at up and down predictions. Is the Amazon stock going to go up or down in the next day? Just that. And just using closing prices. And we actually use several stocks, but that doesn't matter too much. And we have several machine learning algorithms. And so if we were doing a bandit style, where we're just going to choose one, well, we choose the blue one, which happens to be a random forest. And then if we're going to do calibration, we say, well, if we're going to calibrate, the way we'll calibrate is, because these algorithms actually say how much they think the stock will go up or down, we're just going to say we're going to make a prediction only if it's predicted to go at least 1% up or 1% down. And then our reliability becomes better, but of course we refuse more. So just those two notions of choosing a machine learning algorithm, eventually weighting it, but right now just choosing it, and then some kind of calibration notion can give us a nice accuracy. Of course, we haven't tested this with in a massive level yet. The other experiment that we have done, which I'm not showing you, I told you that those handwriting recognition and forest cover, those were all IID, but we can artificially change them. So now, when instead of recognizing the number 2 as 2, I call it 8, and I call 3 9, and 4 1, and so on and so forth. So let's say I change that in the middle. Then this architecture that I showed you will adapt to that. It'll start refusing more and more. Mainly the safe predict model will refuse more and more, and then eventually it will recognize what used to be a 4, it'll recognize it as a 1. So it will adapt to the change. Okay, so this is the last slide. Refuse to predict sometimes can help. The experiments show that this is at least promising. Any questions?
So, what is when you adjust the parameter to refuse? Can you quantify how long you will refuse in order to discover the new concept to drift over?
So, okay, Is there no way that the sound engineer can make that not happen anymore? Anyway, yes, so great question. So the question is, I will repeat it and hopefully without squeaking. So if we start to refuse, how do we get back, I'm paraphrasing, how do we get back to starting to accept again? And how long does that take? Well, it is indeed a parameter that one has to fit, but basically our essential idea, and this is a published paper so you can get to it and you can ask me about it if you want, but the basic idea is we do something called weight shifting. Again, weight as in W-E-I-G-H-T, weight shifting where we sometimes accept, even though things have been bad, we sometimes accept the prediction anyway. And if that starts to work out, then we start accepting more and more and more. And so the basic idea is that we, if you look at the whole history, in the case where we're changing the handwriting example, what will happen is if we send the error up, then we will refuse. When the error goes down again, then we'll start accepting pretty quickly. Now, what pretty quickly is, will depend again on those parameters, but it's pretty good. It tracks things quite well. So that when our error rate is low, it will continue to accept, and when the error rate gets high, we won't, but we'll come back to accepting when the error rate gets low again. Because remember, even if we've changed those algorithms, even if the labeling has changed, that 4 became 1, for example, the underlying machine learning algorithms will adapt because of all the methods I told you about before, and so they will eventually call 4 1, and then the safe predict will start accepting. Yes.
So I think about, this is fascinating. I think about how this applies to the financial markets, and I love going back to the turkey analogy, which is the only place it doesn't work. But it doesn't work in the turkey analogy because the turkey's dead. There's a lot of places in financial markets where you're maybe not the turkey, but maybe you're the turkey's brother or cousin, and you see what happened to the turkey. Maybe you have to react really quickly. So fight or flight. How close, I guess, this obviously works very well for the prostate. How close to that turkey regime can you get? I don't know exactly how else that's.
I think it's a beautiful question, and thank you for expanding the turkey parable. I really like that. Well, again, the experiments that we've run have been those experiments where we change the labeling. And so in that case, as long as you're pretty stable about when you're changing the labeling, you change it and then you're stable for a while, then it will start predicting again. And so if I'm the turkey's brother, or cousin, I'm going to go, oh geez, all that beautiful garlic I had, it may not be a good sign after all. And then, I don't know what the turkey can do about it, but at least it will predict that maybe life won't be so good.
Professor, how does this concept, drift concept, addresses the biases that are built into these machine learning algorithms, right? We see them, that certain algorithms are trained in with certain data set, and you see the biases in the output results. And I think a few days ago there was an example on the Apple Card that male applicants were getting higher limits versus females. So do you think the drift, the concept of drift will address the built-in biases, or it is a separate problem altogether?
I love the question. I don't have a good answer. Because I guess, so if the problem were to see whether one group was getting favorable treatment over another, I think one would have to deal with that more statistically than through the machine learning. In other words, one could look at these outcomes, which is what people did for the Apple case, look at these outcomes and say, wow, this is just bizarre. Statistically, this should not be happening. The null hypothesis should be that anybody with equivalent income should get the same credit limit, and if that isn't true, we can just do a null hypothesis test, and I always like to do things non-parametrically, and then decide. So I don't think it's a machine learning or concept drift issue. I think it's more of a hypothesis testing issue afterwards, where the null hypothesis is that there's no bias, and then you might discover the bias. Oh, time. Okay, so thank you very much. It's been a pleasure.